This is about the approximation of a continuous function with polynomials. This is a very remarkable result due to Weierstrass. It's called the Weierstrass approximation theorem. I'm going to give a simple proof of it. Okay, first of all, there's a little estimate here. Remember, these are the binomial coefficients, m things taking k at a time. And I'll have k minus mx squared, x to the k, 1 minus x to the m minus k. And here x is going to be in here. And what I can say is that for all x between 0 and 1, this expression is less than a constant times m. In fact, you can let the constant be 1/4. Okay, so I'm going to show you this result. First of all, if I take m over k times k, it's m factorial over k factorial times this times k. This thing is, of course, the binomial coefficient. So I have the m out here. I'm going to take the m, the top m from the m factorial, bring it out, and write m minus 1 factorial. And then that k cancels with the top k here, and that gives me k minus 1 factorial. And then the m minus k I will write in the form m minus 1 minus the quantity k minus 1. And so if I look at what I've got here, it's just m times m minus 1 things taken k minus 1 at a time. Similarly, if I take m over k times k minus 1, it equals to this. And now I'll factor out the m and the m minus 1 from the top two factors of m factorial and retain m minus 2 factorial. And the k minus 1 will cancel with the k and the k minus 1 of k factorial. So I have this. And now for the m minus k here, I'll write it as m minus 2 minus the quantity k minus 2. So if I look at what I've got, it's m times m minus 1 times m minus 1 things taking k at a time. See, the binomial coefficient here. All right, so here's the thing. If I look at this here, where I have a k and then an x to the k times all this, all right, what do I get? Well, I have k times this. That's equal to m times m minus 1 k minus 1. See, right here. There it is, see? And now I'm going to take the m out, and I'm going to remove one of these x's and take it out. And now I'm going to rewrite this m minus k as m minus 1 minus the quantity k minus 1. Now at this point, I will change the variable of summation. So instead of letting k go from 1 up to m, I will let k go from 0 up to m minus 1. And everywhere I see a k, I will put a k plus 1. So then this whole mess gives me the same sum as this. And now, by the binomial theorem, this is really just 1, because it's x plus 1 minus x raised to the m minus 1 power. So this whole thing reduces to mx. Now let's look at this one. Well, for this one, I'm going to use this formula. So I use it, and I factor out an x squared from the x to the k. And the sum, of course, starts from 2 and goes up to m, because the k equals 0 and k equal 1 just give you 0 here. And then I'll rewrite the m minus k as m minus 2 minus the quantity k minus 2. And now I'll change the variable of summation. So k will go from 0 to m minus 2. And everywhere I see k, I'll put a k plus 2. And then I get this. And in the same reasoning, this is x plus 1 minus x, all raised to the m minus 2. So this whole mess is just 1. And so you get this. Okay, now if I look at k minus mx squared, now where is that? That's right in here, isn't it? If I look at that and I multiply it out, this is k squared minus 2k mx plus m squared x squared, and that's k times k minus 1 plus k times 1 minus 2mx plus m squared x squared. So this expression I'm trying to estimate will be equal to this plus this times k x to the k times this plus this. And from what we just discussed up here, we get an mx for this one and a m times m minus 1 x squared for that one, I get this. Now if you simplify that, it's m times the quantity x minus x squared. Now if you go inside here and complete the square, you'll see that the biggest this can be is 1/4. This is not terribly important. If you want, just pretend there's a plus sign here and make them both equal to 1 and say 2m. That would be a cruder estimate, but we don't have to be very careful about the estimate. The only thing that matters is that you get an m here. Okay, the Bernstein polynomials are right here. We have a continuous function defined on the closed interval from 0 up to 1. P sub n is going to be this. So you have f of k over n, x to the k, 1 minus x to the n minus k. Okay, so then your f of x is equal to f of x times all this. Why? Well, because all this is just a fancy way of writing 1. So I move the f of x inside here. Okay? And so if I look at p sub n of x and subtract it from f of x and take absolute value, then by the triangle inequality, this is smaller than or equal to this. Now I take a look at this sum, and I break the sum up into two pieces. I want to look at some k values of k where k over n is close to x, and other values of k for which k over n is not so close to x. So what I'll do is I'll measure that closeness with delta. So this is smaller than or equal to this, where x minus k over n is less than epsilon of all this stuff, plus this, and that's where x is further than or equal to delta from k over n. Okay? Now, since f is continuous on this compact set, it follows that it is uniformly continuous. So there exists a delta such that if x minus y in absolute value is less than delta, then this is less than epsilon over 2. This is the auspicious choice for delta. So if I take a look at this one here, x is closer to k over n than delta, and so this will be smaller than epsilon over 2. So I get the first integral like this. Now this second integral will be smaller than 2m, where m is the largest value of the absolute value of x on this interval. You see, so if I look at this, it's smaller than 2m here, see? And that's pretty crude. All right, so I have 2m, and then I have this times this. And now what I will do here is I will multiply every term in this sum by something that is bigger than or equal to 1. And this is that thing. See? Because if I look at k minus nx, see, look over here. This is what we're looking at. So if I multiply both sides of this inequality by n, I'd get nx here minus k, and then this would be n delta. I'd square both sides, and you see this thing, nx minus k quantity squared, would be bigger than or equal to n squared delta squared. So this is bigger than or equal to 1. Okay? And now what I'll do is I'll include more terms in this sum. I'll just forget about this condition and toss in a few more positive terms. That will only make it bigger. And so what I wind up with is epsilon over 2 plus 2m over n squared delta squared. And then I have this thing. But I've got an estimate on this. This thing is smaller than n over 4. So I find that this is smaller than or equal to this. And that, you see, can be made smaller than epsilon over 2, this thing here, simply by making n large enough. So I'll let it be sufficiently large that this is less than epsilon over 2. And then it follows that for n this large, this is less than epsilon. Now, the thing you notice is that this is true for all x in the interval. And so if I want, I could say the maximum over all x in that interval of this is less than or equal to epsilon. Okay, that is the Weierstrass approximation theorem for the unit closed interval. But once you have that, it's easy to get the general theorem. First of all, let me point out what this says in a little different form. This says that p sub n of x, this Bernstein polynomial, converges to f of x uniformly as n goes to infinity. Okay, so the general result is this. If you have a continuous function on an interval, then there is a sequence of polynomials which converges uniformly to f on this interval. Well, so here's how we can prove it. For t element of 0, 1, let h of t be a plus b minus a times t. So h maps 0, 1, 1 to 1 and on to ab. So if I look at f composed with h, it's a continuous function defined on 0, 1. So there's a sequence of polynomials p sub n that converges uniformly to f composed with h on 0, 1, like so. And now h is 1 to 1 and on to, so for all x element of AB, I can look at t equal to h inverse of x, see, and write this down, and this will be less than epsilon for all x. Now, this is obviously a polynomial because h inverse, see, here's h of t, and if you solve for t, make this x, solve for t in terms of x, you find that h inverse of x is this. So if your polynomial is of this form, it follows that your polynomial of h inverse of x would be something like that, and that's clearly a polynomial. So that proves the Weierstrass approximation theorem. Now, he didn't prove it this way. It was philosophically like this, but he used integrals instead of sums. I'm not sure when these Bernstein polynomials, I suppose Bernstein did it, because they're called after his name, but they give the easiest proof. And it has an interesting little issue. You can talk about polynomials in z, where z is a complex variable. And so it would be natural to ask whether a continuous function of a complex variable can be written as the uniform limit of polynomials. And unfortunately, polynomials in Z. And in place of an interval, you would have, say, a box or a disk or something. And unfortunately, you cannot do that. The only kind of functions that can be uniformly approximated by polynomials in the case of functions of a complex variable are functions that are differentiable. And that shows that this major theorem of Weierstrass is a strictly real analysis phenomenon. Now you can generalize it to continuous functions of many variables without any real serious trouble. Okay, so that's all for this chapter. So we will quit here.